Welcome back to Algebra 1 with Miss April. We are in Chapter 7 and we are looking at radicals. All right, so we can express rational exponents as radicals, and you saw that in the last chapter. So if then I am given something like this, where my exponent is in fraction form, I can express that as the n is the root, the x is still the base, so it's the base of the exponent, it's the base of the radical, and then we can put the whole thing in a parenthesis, and we did this. You remember this, right? We pulled out that m and we were left with something like this. Well, there's one little step, intermediate step that I didn't put here, where we took the m out, right? And we were left with and then the m was here, right? And then we went to this step. All right. Regardless, this can be expressed in a different way as well. We can take this m that's on the outside of the parenthesis and express it under the radicand with the x. There's a root, and we can do that. Either way, all three of these things mean the same thing. They have the same value. So let's do this with a number that might make sense. Let's try 27 raised to the, whoops, would be the first power. It would be too easy. To the 2/3 power. So remember that you have the m is 2, the n is 3. First thing I want to do, I can think, let's extract that 2 from the numerator, stick it out there. So then under the radicand, remember my n, which is 3, is my new index. And I have the 27, the 27 here. And so that exponent 2, I can't just toss it down there. I can put it on the outside of everything, or I can toss it in there. So now the first thing that I need to do is find 27 squared. And when I put that in my calculator, I get 729. All right. So now then I can find the cube root of 729, which the calculator yields 9. So the answer to 27 raised to the 2/3 power is 9. All right, I hope that example was helpful. Sometimes we will have something in a parentheses that has a variable with it, and that entire thing is raised to a fractional power. So we have to think, remember that n is 4 here, m is 3. So ultimately, if I were to skip the next step, but maybe I should just show you anyway, I remember we're extracting the 3. So I have a 10x, and that's going to be raised to the 1/4 power. I'm going to pull the 3 out there. Okay. Now I should be able to not do this step, but know just by looking at the given that the 4, this is the 4th root, right? N is 4, that's my index, and my base is still the same, 10x. Now, again, I have the choice of taking that power of 3 and putting it under here, or enclose the entire thing in a parenthesis. So I'm going to put it there because it allows me to go ahead and take care of that. When I go to simplify this, note that I messed up on how I should have represented that. Because the 3 is on the outside here, that means that it applies to everything within the parentheses. So when I put it under the radicand, I have to put parentheses there. That way the 3 applies to the 10 and the x. So essentially 10 to the 3rd and x to the 3rd, all to the 4th root. Okay? And maybe it makes more sense to look at it that way a little bit. All right. Well, what's easy to solve is 10 times 10 times 10. Remember, that's 1,000. 1,000x to the 3rd. Now, there are a couple ways to look at this x to the 3rd. Whenever you have, let's see, you have a square. I'm going to write the 2 there because I want to show you something. If I have x squared raised, I have x squared, and it's under the radicand, and it's being squared. Okay, geez, this is confusing. I have x squared under the radicand, and I want to find the square root. So we do know that these are inverse relationships, and these are both n's, so n equals 2 in both of these. So they cancel each other out, and we just have x. So now, if by chance I had something that looked like this, I could conceivably break it up into times x squared, and then it would be x times x, and then that would be x squared. Now, I don't want to get too deep into that part, but I wanted to let you know that they are inverse relationships, and that you can sometimes move them into, break them up into 2 or 3 if you need to, in order to, sort of cancel out. And then you just have x. Here, though, is a little weird. We have the 4th root of 1,000x to the 3rd. So the 4th root of 1,000, well, I didn't pick a very good number. That is about as simplified as you can get, unless you really want to put some extraneous decimal place value under your radicand. So let's go with another example. Let me find one from your book. Let's look at exercise 7.1 and number 4. We have 16z to the 4th power, and that's in the numerator. Then 49x, that is a 9, a raised to the 8th power y to the 2nd power. And the whole thing is being raised to a fractional part. All right, so we can apply that 1/2 power to both the numerator and then the denominator. Remember that the nth root is 2 here, whether we write it or not. Okay, now looking at the numerator, I want to break these individual parts down, and the last video we went over the rules for exponents, which show us that we can't do this. I'm going to write it underneath. So I have the square root of 16 times the square root of z to the 4th. And that's over the square root of 49 times the square root of x to the 8th times the square root of y to the 2nd. And I'm going to put my little 2's there because those are variables under the radicand as a base, and I'll show you why that's helpful. I can solve 16 squared, or the square root of 16, and that's 4. And I can solve the square root of 49, which is 7. So now I'm going to take the square root of z and write it as 2 different square roots. And you can maybe see why I did that, because I just showed you what we can do, right? Now, why can I do that? Because z squared times z squared equals z, where we are adding those exponents, and z to the 4th is what I have here. So we have this rule that allows us to break things up. You have to follow the rules, but now my z's are free. And a z times a z basically leaves me with a z squared. Okay, so in the numerator portion, what do I have? I have that 4, and I have a z squared. Let's take a look at the denominator. We have x to the 8th power. Well, essentially, I can break those up into x squared, and I can keep doing this, right? And this is one way to think about it. X squared. Okay, so what happened? Those 2's, the index and the exponent cancel each other out. So now I'm left with an x to the 4th power. And I can put that along with my 7 over here. I can show you, I'm going to show you another way to think about it in a minute, but this is sort of the simplest thought process here. So what do I have left? I have that y squared. Well, those 2 can't cancel each other out, so I have a y. So this is your answer. Now I do want to mention that when we have something that looks like this, as we did up here, you can think that because it is the same thing, use your index as n. Okay, this is m. 4 divided by 2 is 2. And that's what we got here. So if that makes sense to you and you don't have to draw it out like I did, that's fine. Let's move on. Now remember we talked about product and quotient rules for exponents. There are product and quotient rules for radicals as well. So I have my index to the nth power, and I'm multiplying x times y under the radical. And just like you saw me do, we can break these up. Pardon the ambulance. Into 2. And that allows us to simplify things a little more. And also, if the entire fraction is under a radicand, right, we have the ability to break it up into just showing the numerator and the denominator. And that's helpful for perhaps we can find the square root of something in the numerator, but not the denominator. And so the denominator remains in radical form. So let's do a practical application of that. If I have something like this, right, this is a square root. I didn't write the index. So I can break it up into 25, the square root of 25 over the square root of 49. And that's 5 over 7. Now, let's say I have 25 in the numerator, but I have something like 32 in the denominator. I break this up. And we get our 5 over 32. Now later you will learn something called rationalizing the denominator, because we don't want to leave radicals in the denominator. But for now, understand the rule, okay, what we're allowed to do. You have a problem in 7.2. Let's do this as an example. Let's choose one that looks a little gnarly here. How about number 18? That looks like a lot of fun. So we have 5a over 9b times the square root of 80 a to the third b. Okay, understand that the fraction before the radical represents multiplication of the fraction and the radical. There's no other operation in between them. So you have to kind of imagine the radical as being a type of enclosure, just like if it were something like this, right? You'd say, okay, 5x, we're multiplying that by x. Same here, 5a over 9b is being multiplied by the square root of 80a to the third b. All right, so now that I've said all that, let's talk about where to begin with something like this. Well, let's begin with the radical, because there's nothing to simplify in the fraction at this time. If we were to put 80 in our calculator to find the square root of it, we'd come up with a long decimal string of numbers, 8.944271191. That's not okay, right? So we're not going to put that under the radical. What we have to think about, since this is a square root, we have to think about what can we multiply what two numbers can we multiply together where one of them is a perfect square? What are perfect squares, Miss April? Well, hopefully 1 times 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, and so forth. And so these are our perfect squares. And if I were to think about one of these numbers, could I use one of these perfect squares to multiply by some other number to get to 80? May as well just keep going here. Okay, that's pretty good. And sometimes it's nice to just write those down the side of your paper. You do want to memorize them. But if you write them down the side of the paper, then when you're doing problems like this, it becomes helpful. Well, I can ask, other than 1, that's not going to help anybody. Well, not at this time. So, 4 will go into 80, right? How many times will 4 go into 80? Well, they will go in 20 times. So I can use 4 and 20. 80 is not divisible by 9. Is 80 divisible by 16? It actually is. 5 times. That's going to be our best bet. Whatever the largest number is that you can break it down to. So I can break this down to, I'm going to put it under it, as 16 times a 5. And I'll go ahead and break down, we have the square root of 3 and the square root of b. Okay, so what can be solved here? Well, the square root of 16. Can't do anything about that. Square root of 5. Now, remember, I can think this, right? Where those cancel out, and I just freed an a from the radicand, although I still have 1 remaining. Okay, and then the b. And let's put these in an order that makes sense. Whatever's not bound under a radicand, we can group together. I'm going to go ahead and put these over here. 9b. And then I'm going to take what is in the radicand, and I can go ahead and group them back together. So that's times 5ab. You can think of it like this. All right. Now, as far as what can be simplified now, I have a 5a times a 4a. I can combine those. So I get 20a. And I can put my numbers that are trapped under the radical over the 9b. So I can write it like that as one fraction, or if I want to keep the radical separated, which some people prefer to see, then I can put the 20a over the 9b, and then kind of put the radical like this on the side. Either of those are acceptable and correct. All right, moving on. Now, let's talk about those denominators that have radicals. So we call it rationalizing the denominator, and it's simply removing the radical from the denominator. We want to have our radicals in its perfect nth power form
simplified. So this means that we cannot have a radical in the denominator. So let's talk about how to go about removing that. All right, so let's look at something like 1 over the square root of 4. In order to rationalize the denominator and get rid of that radical, we have to multiply the denominator by this square root of 4 and the numerator. Remember, the law of equality that keeps everything fair states that what we do to the denominator we have to do to the numerator, okay? What we do to one side of the equation we have to do to the other side. We're keeping everything fair. So here, we're not changing the value because we're multiplying both the numerator and the denominator by the same number. It's kind of like if I have 1/2 and I multiply both by 2, then I wind up with 2/4. Am I still talking about the same amount? Of course I am. I just made my values larger, but it's the same proportion. So when I do this, I could represent this new denominator like this, right? Because it's the square root of 4 times the square root of 4. Now remember, there's a 2 here, and they do cancel each other out. So although I do have a square root of 4 there, so now my new value becomes the square root of 4 over 4. And that is how you rationalize the denominator. Perhaps you have something like, let me think of, let's say 16 over, let's do 6, and we'll do a square root over the whole thing, okay? So then, remember, our rules allow us to break this up, where we can do a 16 here and a 6 here. Well, we can find the square root of 16, and that's 4. However, the square root of 6 remains. We need to rationalize that denominator, which means that we need to multiply it by another square root of 6. And we do the same thing up here. Now, remember, that's the same thing as saying, we cancel this out, and we're left with a 6. And then up here, we have 4 square root of 6. And that's how we would answer that. Let's take one of your exercise questions. Let's find a good one here. Okay, how about 7.3? And let's do number 16. You have a 3x over a y, and you have the cube root of 4y to the 4th over x. Nothing to do with that fraction on the outside of the radicand yet. Let's deal with what's in the radicand. And the first thing that we can do is just break this up. So I have a cube root of 4y to the 4th over a cube root of x. And that's being multiplied by this 3xy. I don't want to forget that it exists. So what can I simplify? So if I break this down, I have the cube root of 4, which I can't do anything about, times the y to the 4th. Now, I can break that down into y to the 3rd times y in each of these are being cubed. Now, hopefully you can see that these cancel out, and then that frees a y. And there's nothing else really I can do with the other terms. So I have the cube root of 4 and y. Y is on the outside there. So now the denominator, there's really nothing I can do with that either. So I'm going to put that back over here. Now let's bring it alongside of our other terms. It's y, the cube root of 4y, and the cube root of x. Now, I hope that you can see that these y's can cancel each other out because it's essentially being multiplied. If it were being added or subtracted to something, then that would break the rules for me to do that. But because it's being multiplied, it's not trapped inside a radicand. It doesn't, it's not trapped inside a parentheses with an addition or subtraction. I can do this. So, it's a little more simplified, but this is what I have. All right, and then it's over the cube root of x. In order for me to rationalize the denominator, I can either think that it needs to look something like this so that I can eliminate it. But sometimes what happens when you do that, you forget the steps that you need to take. What is the cube root of x cubed? Well, that's basically, I need to multiply it by cube root of x times cube root of x. You see how that happens, and now I have 3 of those, and that's what this represents. So if I do that to the denominator, I absolutely have to do that to the numerator. Okay. So what that does in the denominator is free the x. Now up top, we have essentially this times 3x times the existing cube root of 4y. Well, the first thing that I want to do is go ahead and eliminate these x's because they are being multiplied, and I can do that. So now I have nothing in the denominator, and let me figure out how to rewrite this in a way that's going to make sense. Well, first of all, this can be moved down there because it means the same thing. And I want to put my 3 up front because it's not in a radical. So if I have the 3 times the cube root of x squared times the cube root of 4y, my rules allow me to combine these 2 cube roots. And for simplification purposes, that's what I need to do. 3 times the cube root, and I'll put the number first, 4, and then I will put my variables in alphabetical order. And that right there is finally the answer. takes a little work to get there, and you need to understand your rules. So, work on these. Make sure you can complete all the exercises and bring me your questions. All right. I will see you for Chapter 8.